Welcome back. Now we are at part 10 of this series of screencasts, and we are interested now in finding the general solution of the wave equation. So the wave equation is what we derived in the previous screencast. I invite you to watch it. It's pretty short, and I think it's very illuminating. Now we are going to dig a little bit deeper into how to find a solution to that equation. This will actually keep us busy for the next few screencasts. But let's take one thing at a time. We are going to look at the general solution and start to develop an intuition of what are the possible physical solutions of that equation. But before we do that, let's rewrite the equation that we had on the previous screencast in a slightly different form, where I replaced q's by the wave function psi. The wave function is essentially a disturbance to the oscillating medium. That's what it is. So the Q is an example of that. Again, let me remind you that rho is the density and tau is the tension. Usually we do not write the equation exactly like this. We make one little substitution, which is just related to a definition. And in fact, the way we usually write it is this way. Where we have the second derivative of the wave function with respect to position minus 1 over the velocity square times the second derivative of the wave function with respect to time is equal to 0. Now, we simply define v, the velocity, as the square root of tau over rho. Now, it's okay to write this, but we know nothing about the velocity. We just know that the way the equation is written like this, it's indeed velocity is as the right units of meter per second. But this is basically the only thing that justifies writing it as the velocity. But what we are going to do in this particular screencast is to examine why we can call this a velocity. And this is what we're going to spend our time doing. I think that this screencast is fairly pivotal in understanding the propagation of waves. So let's do this. Nothing really complicated other than partial derivatives and chain rules. So let's do this. Now, we are going to introduce two different variables. So instead of using x and t, we want to use variable psi and eta. And I apologize, we're using eta here, but the eta here is not the same eta as we used in the previous part. It is not the general coordinate, it's just another variable. Maybe we are running out of Greek symbols, I don't know. But we are usually using psi and eta, psi being x plus vt and eta x minus vt. And once again, we know v is a constant, right? It's related to rho and the tension. Depends on the problem we're looking at. And again, in terms of units, we are fine, right? Because x plus vt is certainly the dimension of a distance, no problem, and x minus vt as well. So we are going to spend the next 5 minutes doing derivatives, really. So let's do it, because we know we have derivative with respect to x and t, and we are going to try to express them in terms of derivative in terms of psi and eta. And for that, we use a chain rule. So when we have to calculate the first derivative of a function with respect to a variable x, we can now express it as a derivative with respect to psi and eta in this usual way. That's not really surprising, right? Because we know x depends on psi and eta. And we can very easily substitute the derivative of psi with respect to x, right? This is pretty straightforward. This is actually 1. And the derivative of eta with respect to x, it's also 1, according to the equation that's written on the top of this slide. So that's very nice. The first derivative is this. Unfortunately, or fortunately, if you like to do derivatives, it's the second derivatives that matter in the wave equation. So we actually need to calculate the second derivative. And the second derivative will be the first derivative of the first derivative. So we're just calculating the first derivative, so we can do it this way. And the operator d over dx can be expressed in terms of derivative with respect to psi and eta. So that's what we do here. So really we just replace the d over dx by d over d eta times d eta over dx plus d over d psi times d psi over dx. And one more time we distribute the various things and we obtain this very simple equation where we took advantage of the fact that dxi over dx is 1 and d eta over dx is 1 as well. So we obtained this equation. Okay, this is not super complicated. Another example of where you can pause the screencast and convince yourself this is true. In fact, I strongly recommend that you do this at least once yourself without looking at the slide. Now, this is the second derivative with respect to position, and now we have to do the same with respect to time. So let's do it. We can also show this expression here. Once again, this is just by partial derivative, and now instead we have that dxi over dt is no longer 1. It's actually v or minus v if we use xi or eta. So this is what we obtain. And we do the second derivative as well. And for the second derivative, we obtain the same expression. These expressions, when looked at on a screencast, look a little bit barbaric, but this is really straightforward if you do it on a piece of paper. And you find that that derivative divided by v squared is actually equal to almost the same as what we find for the psi over dx squared, but not quite. Because remember when we had in the previous slide is that instead of having minus 2 of the cross derivative, so the piece at the center, we had plus 2. Yet the two expressions should be the same according to the wave equation. So we can actually compare the right-hand side and the left-hand side, and we actually look at this. So what we find is that in order for this equation to be always true, the cross derivative, so what I call the second derivative of psi with respect to psi and eta, has to be equal to 0. There is no other way because of the minus sign in front of the 2 on the left-hand side and the plus sign in front of the 2 on the right-hand side. The only way for this equation to be true is that this cross derivative is equal to 0. This is actually an extremely important result. This is an extremely important result because if we write the wave functions, the deformation of the medium, as a function of x plus vt or x minus vt, which I remind you were psi and eta respectively, the solution will never involve a term that's as a product or a complicated or more complex function of psi and eta. So the solution of psi has to separate solution psi and eta. If they did not separate, the partial derivative involving both psi and eta will be different from 0, but we know it has to be equal to 0. In other words, to put it mathematically, and this is an important result in the red box, the solution of the wave equation is a sum or a function of psi and a function of eta, but not a function of both. Because a function of both would yield a cross derivative that's not equal to 0. So that's extremely, extremely central to actually wave physics in general. Okay? Now, if we remember what psi and eta are, which is x plus vt and x minus vt, what we have is this equation. So it looks like the solution is a sum of two equations. Now, it's time now to understand what the velocity is. And for that, let's try to look at x plus vt for a second. And for that, consider the first graph on the right-hand side. It's an animation that I'm going to start in a second. And imagine that you want to follow the top of one of the peak of the blue curve. And as the time evolves, and suppose that v is positive, when time evolves, vt is going to increase. But if I want to stay at the same point on the curve, so in other words, if I want x plus vt to be the same, x has to decrease, right, since vt increases. So I'm talking about f here, just to be clear. So that means that when time evolves, I need to go to the left. So in other words, f of x plus vt is actually a function that's actually moving to the left. It's a function that's moving to the left with velocity v. So V is really the solution of this function that moves to the left. It's very interesting, very important. Now we can do the same exercise for g of x minus vt. As the time evolves, okay, vt is smaller and smaller, but if I want x minus vt to be the same, again, because I want to sit on the peak, for example, I have to move at a larger and larger x. In other words, it has to move to the right, just like this. So it's moving to the right. So you see those two equations, fx plus vt and gx minus vt, are traveling waves. The first one, f, moves to the left, and the other one, g, moves to the right. So the solution of the wave equation can always be expressed as the sum of traveling waves to the left and to the right. And again, I insist that you will never find a solution that's the product of the two, because if there was a product, the second derivative with respect to both of them, to one of each, I would say, would be different from zero. So that's a very important result that we have. So this disturbance psi that we call Q so far in this course will actually be a sum of those two traveling. So this is very nice. So we conclude, and the text that's on the slides is actually what I just said here on the screencast orally. So this is it's pretty straightforward. We see that the solution of the wave function is can look at the composition, the superposition, should I say. Superposition is when we have a plus. So the superposition of a traveling wave to the left and traveling wave to the right. In the example I showed you with the animations, those two curves actually are the same. F and G are actually the same function, but they don't have to be, of course. They don't have to be. Here that just shows them to be the same. So just to make sure that we understand what we are doing, let's apply this to the string. And imagine for time t equals 0, we decide to write a function f of x plus g of x. This is essentially your initial condition. One example that we did in a couple of screencasts ago is that this plug, when we did the plug, the triangular thing. Now we can actually do this as well. We can actually, for example, look at this deformation. It's not exactly the same plug as we did previously, because previously the plug was extending all the way to the end. Here it's in the center of the string. So at t equals 0, qx0, fx plus gx, we can pick, for example, this example of a triangular form. It doesn't have to be this. And what happened is that the solution, the time solution, so the evolution with time of this solution can be decomposed as a wave moving to the left and a wave moving to the right. And in fact, if you solve the equation as we did a couple of slides ago, or a couple of screencasts ago, where we could calculate the mu and the nu as a function of initial condition, you see that indeed, as you see the time evolving, you have a piece moving to the left and a piece moving to the right, which is exactly the way that we expect it to be for our wave that we are looking at as the solution of a traveling wave to the left and a traveling wave to the right. Now we can go a little bit further, and this is how I'm going to wrap up this screencast here. Imagine that you have this formation moving to the left. So look at the panel A. So this is, of course, again, a picture that was taken from the textbook that we are using, the Thornton textbook. Do not worry about what happens in the dashed line for now. That wave is a wave moving to the left. Now it reaches, just at panel B, it reaches the boundary. As we know, at the boundary, the deformation has to be 0, since the string, for example, is stuck there, so it's not allowed to move. So the only way for this to be true is that if there is another wave that's written in dashed line, that's moving to the right, it's an imaginary wave because, of course, there is no string there, so that the sum of the two waves is equal to 0. Right? It's the only way that to happen. But here is where things are interesting. It looks like the initial wave keeps moving to the left. This is what you see in panel C, while the other one that was needed for the boundary condition keeps moving to the right. And what you see here is exactly how you can develop an intuition about reflection. So you have a wave moving to the left. It's actually reflecting on the at the boundary. It actually changes sign. It has to go down and keeps moving to the right. And this is exactly what happens in reflection. So all this is actually embedded in the solution of the wave equation. Sorry. So there is much more that we are going to do with this wave equation. But please do not try to be stuck too much with the math. Instead, try to develop the intuition of and having a picture of what's going on. And I think that using just a few fundamental principles, like the one we described in this screencast, can go a very long way in understanding wave physics in general. Thank you very much for your attention, and I will be posting the next screencast hopefully soon. Thank you.